safe streaming. I'm going to finish the articles today about extended Euclidean algorithm and Lagrange interpolation. And I think I'm gonna watch a bunch of videos about this Diffie-Hellman thing. I finished yesterday watching a video about RSA encryption and checking the rest of the article of the Fermat's little theorem. And now I want to finish these articles here. And I don't know, I studied this, I think, when I was reading the text, but I'm not very familiar with this algorithms here, so I'm gonna have to study. And that's the point of doing the articles, is to study more and understand how they work.
So in previous lessons, you saw that digital certificates solve the problem of public key exchange. And that is good when you use asymmetric algorithm. But when it comes to symmetric algorithm, we only have one key. So how do we exchange that key? If Bob and Alice want to communicate with each other and they want to use a symmetric algorithm, how do they exchange one key that they have? Because if they send it over internet through an unsecure channel, then if someone gets access to that key, then their communication is compromised and it's not secure anymore. Even if you say that what they can do is, for example, Bob can go to Alice and hand over his key to Alice. Then if they have not met each other before, then that's a problem again. How does Alice know that Bob is really Bob and is not someone
I
else?
think I'm gonna start by, in around half an hour I have to eat, so I'm gonna start by reading the article and trying to understand how it works, because I use ChatGPT to build the article. So I'm gonna read it, try to understand how it works, then I watch some of these videos while I eat something. And put some music. I think I'm gonna put Pomodoro study thing here. The field of mathematics is extended Euclidean algorithms is an important concept that plays a significant role in a wide range of applications, including cryptography, computer science, and number theory. It is an extended version of the Euclidean algorithm, which is used to find the greatest common divisor of two numbers. This thing I remember seeing a bunch of different times in a bunch of situations, even like back in the day in school or in college. I think I've seen this a lot, but I don't remember really well how it works. I think it has to do with breaking down, like the name says, finding the divisor between, like the common divisor between two different numbers, and then that has to do with breaking down into the primes usually of the two numbers, I think. In this article, we will discuss the extended Euclidean algorithm in detail, including how it works, its application, and examples. Before I dive into the extended Euclidean algorithm, let's first discuss the Euclidean algorithm. The Euclidean algorithm is a simple and efficient way of finding the GCD of two numbers. It works by repeatedly subtracting the smaller number from the larger number until the remainder is zero. Smaller number from the larger number. So dividing the smallest by the... Yeah, dividing, getting the remainder. No, maybe I'm misunderstanding this. And just is the last non-zero remainder. Yeah, I don't know. For example, to find the GCD of 24 and 16, we first divide the large number, 24. Yeah, that's what I was thinking. Quotient is 1 and the remainder is 8. We then divide the smaller number, 16, by the remainder 8. Actually, that's true. And the remainder is 0. Therefore, the GCD of... Okay. So we get the remainder of the division of the largest by the smallest, and then you divide the smallest with the remainder. And if the remainder is 0, then that's the GCD. If it's not, then I'm not really sure. Understanding the extended Euclidean algorithm. The extended Euclidean algorithm is an extension of the Euclidean algorithm, which not only finds the GCD of two numbers, but also finds the coefficient of Bezout's identity. It's a theorem that states that for any two integers a and b, there exists integers x and y such that ax plus by equals GCD ab. The extended Euclidean algorithm finds x and y in addition to the GCD of two numbers. It does this by using the Euclidean algorithm to find the GCD, then working backward to find x and y. The algorithm works as follows. Let a and b GCD, initialize the variables, calculate the quotients and remainders. I think I'm gonna delete all of this stuff, to be honest, because I don't really care about these things. I wanna more understand the context. I remember that I got the code from this one in one of the Ethereum files, and I wanna understand more the algorithm in that context. I don't really give a shit about all of this stuff. And I work like this a lot of the times, where I think like there is diminishing returns in focusing on stuff that you don't care about, because then like the amount you spend learning is not as effective as you would be as when you're focusing on something that there's a clear end goal in mind. So in this case, the end goal is understanding crypto and how the algorithm works on crypto. So, and I don't really care about the other stuff, so I think I'm gonna learn more about it if I'm invested on it in the context of crypto. So this is the algorithm that I want to understand. And I don't remember where I got this from. I think it was from the research and it has to do with the cryptography part, but I don't remember which project it is. I think I'm gonna explore the projects that I remember seeing something about. Lagrange interpolation. Interesting. I think I have the code for Lagrange interpolation as well. Yeah, that I got from the project. Maybe I'll write down here the C++ version. I think I'm not gonna do that. Just gonna focus on the Python one. I think it was something to do with data sampling, I think. Data availability sampling. Or trusted side. So that implementation is different than this one. Oh, I get it. So you're generating a polynomial that the y is going to be 0 for... What are the other points provided? Like, is this considered to be a point? A set of points, so... Yeah, I don't understand what it means. It has to be 0 at all other points provided. Like how... I don't understand what that means. I guess, like, what I have to do is just multiply x minus the points that it gives here. The multiplication of that generates the polynomial that you want. But I remember there's some stuff about dividing as well. Like, is this thing here then divided by x minus something? That is not on this file. I think I got this one from here. Oh no, maybe not. So maybe I could just search for it. Maybe if I understand, it's probably better to search for the algorithm first, try to understand, then I'm gonna remember where I saw the algorithm. So maybe I'll leave the applications here and then I'll just change this part here.
Bazout's identity. In mathematics, Bazout's identity, also called Bazout's lemma, named after Etienne Bazout, is the following theorem. Bazout's identity let a and b be integers with greatest common divisor d. Then there exist integers x and y such that x plus by equals d. Moreover, the integers of the form a z plus bt are exactly the multiples of d. Here the greatest common divisor of 0 and 0 is taken to be 0. The integers x and y are called Bazout coefficients for a, b. They are not unique. A pair of Bazout coefficients can be computed by the extended Euclidean algorithm, and this pair is, in the case of integers, one of the two pairs such that less than or equal to slash and less than or equal to slash. Equality occurs only if one of a and b is a multiple of the other. Extended Euclidean algorithm. In arithmetic and computer programming, the extended Euclidean algorithm is an extension to the Euclidean algorithm and computes, in addition to the greatest common divisor, GCD, of integers a and b, also the coefficients of Bazout's identity, which are integers x and y such that this is a certifying algorithm, because the GCD is the only number that can simultaneously satisfy this equation and divide the inputs. It allows one to compute also, with almost no extra cost, the quotients of a and b by their greatest common divisor. Extended Euclidean algorithm also refers to a very similar algorithm for computing the polynomial greatest common divisor and the coefficients of Bazout's identity of two univariate polynomials. The extended Euclidean algorithm is particularly useful when a and b are coprime. With that provision, x is the modular multiplicative inverse of a modulo b, and y is the modular multiplicative inverse of b modulo. Similarly, the polynomial extended Euclidean algorithm allows one to compute the multiplicative inverse in algebraic field extensions and, in particular in finite fields of non-prime. It follows that both extended Euclidean algorithms are widely used in cryptography. In particular, the computation of the modular multiplicative inverse is an essential step in the derivation of key pairs in the RSA public key encryption method. Description edit. The standard Euclidean algorithm proceeds by a succession of Euclidean divisions whose quotients are not used. Only the remainders are kept. For the extended algorithm, the successive quotients are used. More precisely, the standard Euclidean algorithm with a and b as input consists of computing a sequence 1 of quotients and a sequence 0 plus 1 of remainders such that it is the main property of Euclidean division that the inequalities on the right define uniquely and plus 1 from 1 and the computation stops when 1 reaches a remainder plus 1, which is 0. The greatest common divisor is then the last non-zero remainder. The extended Euclidean algorithm proceeds similarly, but adds two other sequences, as follows. The computation also stops when plus 1 equals 0 and give is the greatest common divisor of the input equals 0 and equals 1. The Bazout coefficients are and, that is, GCD equals plus.
So I think I get it. Now just understanding how it works on the code there. But I think I understand the purpose, but I'm trying to remember where did I saw this thing. Because just understanding the algorithm, I can't remember. But I think there's a very high chance that it was on stuff that is related to the cryptography. think I'm gonna searching the Vitalik's site and Ethereum research. I think I saved on the favorites here. There's so many good titles here. Good stuff that is interesting. Maybe it was related to this stuff about Friday and the other algorithms. Yeah, I think it was related to zero knowledge proofs. Yeah, Fermat's zero theorem. Yeah, here. So I found it. So I think I'm gonna read this stuff again. I'm not really sure if this is. It seems like it is more related to the data availability sampling thing because of this stuff here. But I don't remember really well if it is related to that or zero knowledge proofs. That's one of them. Yeah, Starks. So it is zero knowledge proofs. Part 3. I don't think I read part 3. So I already understand how it works. It's an algorithm to get the greatest common divisor and also to get these coefficients here. And I think that this makes sense because of the way that is described here, where like because you're finding the numbers that multiply each number, it is equal to the greatest common divisor. So you're solving the linear equation, I think. But I wanna understand how it works here on this code. So what I'm gonna do is put this on ChatGPT. I think I'm gonna erase this part here. Because it isn't very clear to me the way that is written here. I wanna write in a way that is easy to understand what it is and how it works. So I'm gonna erase this stuff. So this part here, I think I'm gonna leave it like this because it is good. And I think I'm gonna put this stuff here. And now I'm gonna put this on ChatGPT and I'm gonna use ChatGPT to hopefully if I can. If I can't, then I'm gonna just figure out on my own. I think it would be helpful to find the page though. I think I'm gonna do that as well. So that I understand what arguments are being passed here. With this A and N. Because I think that's what it makes hard to understand. But I guess it's just the true numbers that you wanna find the greatest common divisor. It's probably what it is. The inverse of a number A modulo N. And modulo N it means that you wanna find the remainder. So we wanna find the inverse of the remainder of A divided by N, I think. Finding a linear combination of A and N that equals the greatest common divisor. Checking if A is 0. If it is, then the inverse is also 0. Um, and the quotient is how many full parts one number has inside of the other. And the remainder is how many it has left, let's say. So getting the quotient here. I don't understand what HM and LM is supposed to be. So here's going to be 1, and then it's going to be 0. So 0 minus. So NM is going to be negative R, but in the first iteration. High is the remainder of A divided by N. Low is the remainder, and high is the number. It's hard for me to visualize what's happening here. So it's multiplying the quotients by the low number, by the remainder. Like, I don't understand why though. Is using this as the boundaries and updating the boundaries until it gets to the remainder of 1 or 0. I don't understand this part here. NM new LM low. Okay. And the thing I don't understand is why he's multiplying by R here and not multiplying anything by anything on this side here. Give him a go, grab something to eat, and watch some videos. So this is gonna be okay. So NM is supposed to be A here. A equals this, but oh, high low goes here. So the lowest common one is the remainder between A divided by N, and the highest is N, is the number itself. And then you do high divided by low. So you do the number divided by the remainder. Think I get it, but I need to clarify more on how it works. And this part's really hard for me to understand. I think I'm gonna go grab something to eat and then I'll watch these videos, and after this we will go back to try to understand. They'll be right back.
Hello again and welcome to this video on the extended Euclidean algorithm. So in the last video we learned about the Euclidean algorithm and what it's for. Namely, it's a process that computes the greatest common divisor of two integers. Here on the screen I have the results of the first calculation we did in that video where we used the Euclidean algorithm to calculate the GCD of 888 and 54. That turned out to be 6. And importantly, I want to look at the steps here. We started off by dividing 54 into 888 and found that it went 16 times with a remainder of 24. To continue the Euclidean algorithm, I shifted the 54 and the 24 into the previous spots for 888 and 54. So 54 is being divided into, and 24 is now the divisor. We can quickly check that 24 goes into that twice with a remainder of 6, and I shift again and divide 6 into 24 and see that that goes in 4 times with a remainder of 0. Now the Euclidean algorithm says stop with the last non-zero remainder, that will be right here, and that's your GCD. So we're going to use this fact that 6 is the GCD of 888 and 54, as well as the results of the process, to do something interesting with this GCD. I'm going to draw a little line right here and work with the two equations you see above that line, starting with the number 6 here. I claim that I can write 6 as a sort of combination of 888 and 54. Let me show you what I mean by that. So I'm going to start off by taking this equation and rewriting it in a slightly different form. I'm going to write this as 6 equals, I'm going to solve this equation for 6, basically. So 6 would equal 54 minus 24 times 2. Now certainly that's correct, because 24 times 2 is 48, and 54 minus 48 is 6. I'm going to rewrite this just slightly one more step here, and instead of saying minus 54 times 2, I'm going to say plus 24 times negative 2. Now, interestingly, if I look up in the first line here, I see 24 hanging out in the remainder spot. Now I can solve that equation for 24, and 24 would be equal to 888 minus 54 times 16. I'm going to put that into this equation over here, where you see the number 24. Let me put this in green. So 24, I could also rewrite as 888 minus 54 times 16. And that was being multiplied by minus 2 from the line up above it. So basically what I've done is I've substituted 24 with something that it's equal to. Now let me simplify some of the math here and explain what happens. Okay, so I have 54 in here. Inside the parentheses, I'm going to do what I did a little earlier and say this is 888, and not subtracting 54, but adding 54 times a negative 16. And the whole group there is multiplied by minus 2. Now if I distributed that minus 2 through, what I have here, I have 54 here, and I would have 888 times minus 2, and then I have to multiply to here as well. So that would be 54 times negative 16 times negative 2 is positive 32. Now I have a 54 over here as well, so in the end, I can write this as 54. How many 54s do I have? I have one here and 32 of them here, so that's 33 times, or plus 888 times minus 2. And this is all equal to 6. Now you can check that this is true, but importantly, notice what I've done here is I started by looking, this whole process, I started by looking at 888 times and 54 and found that their GCD was equal to 6. Using the results of the Euclidean algorithm and sort of working backwards through the Euclidean algorithm, by starting with that last non-zero remainder and successfully doing some solving and substitution, I've actually written 6 as a combination of 54 and 888. I can take 6 and write it as 54 times an integer plus 888 times another integer. This sort of construction right here is called a linear combination. Linear combination of those two numbers, 54 and 888. What I've done here in forming a linear combination of these two numbers is I've taken 54 and 88 and multiplied them by integers and then added them. That's what a linear combination is. And what I see here is that the GCD of those two numbers is actually equal to a linear combination of the numbers that gave me the GCD in the first place. This turns out to be true for every pair of positive integers you can find, that the GCD of two integers can always be written as a linear combination of those two integers. And the process that we just went through, this long process right here of finding the weights that I multiply, these two guys right here, is called the extended Euclidean algorithm. So I can use the Euclidean algorithm to find the GCD in the first place. That's what we did over here. And then if I wanted to, I can find I can use the extended Euclidean algorithm to write the GCD as a linear combination of the original two numbers. And for us, that's going to be actually a very important process. So let's do one more example. Actually, it's sort of a two-stage example. I'm going to look at the numbers 1180 and 482. And first of all, I'm going to use the Euclidean algorithm to find their GCD. When I do that, so this is another example of something we've already seen, but importantly, I need to keep track of the results here. So let's run through the Euclidean algorithm and see what happens. So the larger of the two numbers is 1180. So I'm going to try to write 1180 as 482 times something plus a remainder. This is basically long division, but I'm not going to write the long division out. If you wrote it out as long division, you'd find that 482 goes in twice with a remainder of 216. Now let's shift and see if I can find 482 equal to 216 times something plus another remainder. This remainder right here was not 0, of course, and so the Euclidean algorithm hasn't terminated yet. Now 216 goes into 482 twice with a remainder of 50, so I'm still not done. Let's shift them over. 216 is equal to 50 times something plus a remainder. I can see that that goes in 4 times with a remainder of 16. Still not a non-zero, still not a 0 remainder, so I need to keep dividing. If I take 50 and divide it by 16, that is going to go in 3 times with a remainder of 2. That's still not 0, so I've got, I think, one more step to do with the Euclidean algorithm. Shift again and see if I can divide 16 by 2, which of course I know how to do that. That's 8 with a remainder of 0. The Euclidean algorithm would say stop here and look at that non-zero remainder, that last non-zero remainder. That's the GCD. So these two numbers have a GCD of 2. So what we're going to do now is use the extended Euclidean algorithm to write 2, that GCD is circled in red there, as a linear combination of 1180 and 482. In other words, I'm going to try to find two integers such that 2 is equal to 1180 times one of them, plus 482 times something else. Now, how we're going to do that, again, is to start at the end of the Euclidean algorithm and work our way backwards. I'll do this in red. So let's first of all solve that last equation for 2. This is going to be 2 is equal to 50 minus 16 times 3, but I'm going to write that as plus 16 times negative 3. Again, I've just taken that last equation on the bottom there in blue and solved it for the number 2, the smaller number there. Now, if I work my way up the chain here, what I see is that 16 can be written as 216 minus 50 times 4. So I'm going to substitute this 16 right here with something that is equal to. So this is 50 plus, I'm going to make a substitution that's going to equal 16. I'm already multiplying the 16 times a negative 3. So what goes in here, that is going to be 216 plus 50 times negative 4. Now let me distribute the 3 through, and notice what's going to happen here. I'm going to have 216 times negative 3, and then I'm going to have 50 times negative 4 times negative 3. That's 50 times 12, and I have another 50 hanging out over here. So in all, that becomes 50 plus, or 50 times 13. And if you stop right here and just computed this right-hand side, you would see that it equals 2. It's a useful check. Okay, so now I notice that 50 right here can be written as 482 minus 216 times 2. And so I'm going to do a substitution here of the number 50 that you see right there. So I'm going to create a space for the substitution, keeping in mind that I'm already multiplying all that stuff by 13. Now, according to the second line of my Euclidean algorithm, 50 is equal to 482 plus 216 times negative 2. Now let's check things out here. I have 216 times negative 3, and I also have 216 times negative 2 times 13. So how many 216s is that in all? Well, I have negative 3 right here, and I'm going to have negative 26 right here. So this is a total of negative 29 times 216. And the 482 is also going to be multiplied by 13 once I distribute this 13 through the group. So you can stop right here and check that this equation, this side right here, does actually equal 2. Now, one last substitution step. Okay, the 216 here can be written as 1180 minus 482 times 2. So I'm going to do one last substitution, and I think we'll be close to done. The 216 is equal to 1180 plus 482 times negative 2. And this is all times negative 29. And this is also all plus 482 times 13. So now let's see where we end up here. If I distribute this negative 29 through, what I end up with here is I have 1180 times negative 29, and a lot of 482s. Negative 29 times negative 2 is 58, and I have that many 482s here. 58 plus 13 is 71, so this is 482 times 71. And now, if you notice, I've actually done what I set out to do. This 2 is now equal to a linear combination of 1180 and 482, and I know what the multiples are. This is going to be negative 29, and this is going to be 71. So that's what the extended Euclidean algorithm does. The Euclidean algorithm allows us to go from two numbers and end up with a GCD. The extended Euclidean algorithm starts at the end of the Euclidean algorithm, works its way backwards up through the Euclidean algorithm this way by making a series of substitutions with the goal of writing the GCD as a combination of the two numbers that generated the GCD in the first place. Now, why is that important? Stay tuned for the next video to find out.
Okay, so
today our topic is extended Euclidean algorithm. To understand this topic, you should know what is Euclidean algorithm. And this part I have already covered in my previous video. So get the basic, what is Euclidean algorithm and how to find GCD of two number using this algorithm. Because this video, extended Euclidean algorithm, is just the extension, okay, extension of Euclidean algorithm. So let us understand this by an example. The example is find GCD of 161, 28 using extended Euclidean algorithm, and also find S and T. Okay. So this is the question and this is the exam question. So take a special care. Okay. So let's start the video. What is step one? Step one is creating the table, and table has a lot of columns. So make a note while writing the notes. Okay. So column 1 is Q, column 2 is R1, column 3 is R2. Okay, this is R2, and I will run and I will write correctly. It's R2. Then we have R. So this is exactly same as the Euclidean algorithm, correct? Nothing is changed. Now we have extra columns: S1, S2, S, T1, T2, and T. You can see the 6 extra columns. And there is also some assumptions and equations. So write it down as well. Okay. What is the assumption? Assumption is S1 is 1, S2 is 0, and T1 is 0 and T2 is 1. This is standard assumption given by the extended Euclidean algorithm books. Okay, so this is the standard assumption. S1 is 1, S2 is 0, T1 is 0, T2 is 1. Okay, so what to do next? Next is fill in the values R1 and R2. R1 is what? It's the highest value among the two numbers. The highest value is 161, so R1 is 161, and the remaining part would be R2. Use your logic, which we have already studied in the previous video. 161 divided by 28, so 28 5s are, it is 140. Do the subtraction, the answer is 21. Numerator part is the coefficient part, denominator part is remainder part, coefficient is 5, remainder is 21. What about S? What about T? How to get this value? We have one more equation. Okay, so I will rub this part. I hope you have written this in your notebooks. Okay, now what are the equations? The equations are S is equal to S1 minus S2 into Q, and same goes for T. T is equal to T1 minus T2 into Q, and use this expression to get your value. So what is the value of S1? S1 is 1 and S2 is 0 and Q is 5. So after substitution, S would be equal to 1 minus 0 into 5, which is 1. So value of S is 1. And similarly, you can find the value of T. The value of T is equal to T1, which is 0, minus T2, which comes out to be 1, into Q, which is 5, so minus 5. And I will write here minus 5. Okay, I hope you got your row 1 elements. Now we are moving forward to the row 2 elements. To get the row 2 elements, the same logic we have to use, the logic we use in the Euclidean algorithm. Shifting of the terms. R2 would be shifted at R1 position, R would be shifted at R2 position, S2 would be shifted at S1 position, S would be shifted at S2 position. Similarly, T2 is shifted here and T is shifted here. Okay, so I will write the values. The values are 28, 21, 0, 1, 1, minus 5. How to get the rest element? It's simple. It's simple, literally. What logic we have used in the row 1 elements? We did the division first. After doing the division, we got the quotient and remainder. Okay, once we get quotient and remainder, then we can find value of S and T. The same steps we are following here. 28 should be divided by 21. You can see 28 and 21 are the elements. So 28 when divided by 21, its ones are 21 and this is 7. Okay, so this part is the remainder part. This part is the coefficient part. So coefficient is 1 and remainder is 7. Then you can get the value of S using the equation. So the value of S here comes out to be minus 1. The value of T using the equation, answer comes out to be 6. Okay? You can move further to the next row, which is row 3. How to get the elements? Shifting. Okay, this is not tough. I've already given the steps in the previous video. So the same steps are repeating. Okay, so you can see here the steps, all the shifting versions. So 21, 7, 1, minus 1, minus 5, 6. Do the division. I hope you can do it. I will pause here for some minute. Let us see how many students can solve this. Yes, the answer is 3, then 0, then it's so the value of S is 4, then the value of T, I've written it down, it's minus 23. Okay, again you have to do the shifting, the final shifting, because now we will arrive at a problem. Okay, so this is the final shifting, and yes, the final shifting. 7, 0, minus 1, 4, 6, minus 23. What is the problem? Now you cannot divide it further. 7 divided by 0. You cannot do it. 7 by 0, it's not possible. So if it's not possible, we do not have any quotient, we do not have any remainder, and hence we cannot find the value of s, we cannot find the value of t. So this is the last row, and you have got your answer. The value of GCD is here. The value of GCD is 7. This is GCD. The value of s, okay, this is the value of s. Okay, s is nothing but updated s1, which is equal to -1. This is the value of t. T is nothing but updated value of t1, which is equal to 6. So your final answer is GCD is 7, s is -1, and t is 6. So I hope you got the solution and the process how to find the values of GCDs and s and t using extended Euclidean algorithm. This is helpful and powerful to find the multiplicative inverse of a number. In the next video, we are going to study how to use this concept to find multiplicative inverse of a number.
So I wanted to make a video explaining how to use the extended Euclidean algorithm and use it to find the GCD of two numbers. So let's say we want to find the GCD of 56 and 15. But remember that Bézi's theorem, so for those of you just joining us who aren't taking my class, this is Bézi's theorem. And Bézi's theorem says whenever you're looking for the GCD of two numbers, like 56 and 15, there must always be these integers. Let's call them s and t such that 56 times s plus 15 times t is equal to whatever their GCD is. So this is Bayes' theorem. There has to exist that integer. And that integer, this is actually turns out to be important in computing, for instance. Lots of encryption protocols rely on this computation. And so knowing how to find those integers s and t is useful in a lot of contexts. The nice thing is that the normal Euclidean algorithm that calculates, so remember we use the Euclidean algorithm to calculate the GCD, you can extend it very slightly to also tell you what this s and t are going to be. So this is going to be the extended Euclidean algorithm, and it's a very simple algorithm, very easy to follow. And so what I'm going to do is I'm going to show you how to calculate the GCD of 56 and 15 using the extended Euclidean algorithm. So at the end, we will also know the values of s and t. Okay, so let's get a new sheet of paper here. So we start by, it's going to be helpful to build 3 columns. So in the first column, we're going to run the normal Euclidean algorithm, which I will show you how to do in just a second. In the second column, we're going to rewrite every line from the first column slightly. And in the third column, we're going to build the solution to 56s plus 15t is equal to whatever the GCD is. Okay, so let's see how to do that. So we're just calculating the GCD of 56 and 15. So we start by putting 56 on one side, setting it equal to 15, and then finding the quotient and remainder of 56 divided by 15. So you should be able to see that the quotient is 3, which is going to give me 45, and I have a remainder of 11. It's going back to your fundamental theorem of divided by 15. So you should be able to see that the quotient is 3, which is going to give me 45. And I have a remainder of 11. It's going back to your fundamental theorem of 4th grade. And notice what I've done here. What I've done here is I've underlined the divisor and dividend here, and I have not underlined the quotient. I have also underlined the remainder. And we're going to do this each time, and we'll see why I care about tracking these underlined numbers in a minute. So for now, let's just run the Euclidean algorithm. Remember that what happens at the next line of the Euclidean algorithm is that value goes into that slot, and that value goes into that slot, and then we play the same game. So 15 moves over to the underlined spot, 11 moves over to the underlined spot, and now I need a new quotient and a new remainder, and I'm going to underline the new remainder. So 11 goes into 15 one time with a remainder of 4. Everything moves over one slot. Notice that it's always
The other thing I don't understand here is why the R is declared here inside of this thing. Oh, it's changing the height here. That's why. No, this part that the guy's talking about in the video is this one, but the difference is that HM is not the remainder. It's just 0. Here's the number itself minus low, which is the remainder times the quotient. I don't understand how, like, it doesn't make sense to me. It seems like the videos they're talking about a different equation should determine. The thing is that I don't understand these names here. Like, what are they supposed to be?
the underlying things that are moving, but these ones are just kind of leaving, right? So we have 11 is equal to 4. We need a quotient and a remainder. 4 goes into 11 2 times. 2 times 4 is 8 with a remainder of 3. And do the same thing. So the 4 moves over, the 3 moves over. And now, how many times does 3 go into 4? It goes in 1 time with a remainder of 1. Since we're human, we could tell that as soon as we get a 1, that it has to be the GCD because there's no smaller value. That's the greatest common divisor. 0 isn't the divisor. But if we're really going to do the mindless algorithm, we could run it one more time. So the 3 would move over, the 1 would move over, we would get a 3, and then we would get a remainder of 0. As soon as you see the remainder of 0, you know that the last remainder was the GCD. So the GCD of 56 and 15 is equal to 1, which we found is the last remainder above the 0. And we're going to just completely ignore this last line. The last line just tells us to stop. Okay. So far, so good. But now what we want to do is rewrite every single line here in terms of the remainder. So right now they're written like 4 is equal to 3 times 1 plus a remainder of 1. What we want to write it as is 1 is equal to 4, and then to move that onto the other side by algebra I have to subtract, right? So it's going to be 4 minus 3 times 1. And so if you think about it, one way to do this really quickly is to write out the same equations here, but we're going to leave off the equals and plus for a second. So this is 56 underscore. Do not forget these underscores and make sure you put them in the right place because they're going to be important. 3, 11, right?
It's very confusing to understand. I'm not gonna lie.
This one is 15 underscore 11 times 1 plus 4. This one is 11 underscore 4 times 2 and 3. This is 4 underscore 3 times 1 and 1. And now notice, let's look at this for just a second. So let's isolate it down here. We have 4 is equal to 3 times 1 plus 1. And what we're essentially doing, we want to write things in terms of this equals something else. So what we're going to do is subtract from both sides 3 times 1, which makes this 4 minus 3 times 1 is equal to 1. In other words, it's exactly the same form, but the equals turns to a minus and the plus turns to an equals. So we can use that to do this next step really quickly. All the equals turn into minuses, and all the pluses turn into equals. And you should just make sure, look at that to that line to that line, that line to that line, that line to that line, and convince yourself that all I've done each time is subtracted off the thing in the center to move it to the other side of the equals. Okay. So now comes the interesting part. We have that the GCD is 1. And by Bayes' theorem, we know that 56s plus 15t equals to 1 has integer solutions for s and t. We would like to find them. So you'll notice that this top line is 56 times something, which is a little implied 1 here, right? We always say 56 times something, and 15 times something, so it's times a negative 3. The problem is it's equal to the wrong thing. It's equal to 11. So the right side of this first equation isn't correct. It's not getting me what I care about. What I care about is the right side of the last equation. That's the GCD. And so what I'm going to do is I'm going to work backwards. So this is very important. We're going to start at the very bottom here and work our way up using one line at a time. And I'll just check off the lines as I use them. So you'll know which one do you use next is the one above. And so the thing to notice is, well, let's start. So let's write 1 is equal to 4 minus 3 times 1. And for times 1s, we can just drop them. We'll go 4 minus 3 is equal to 1. Okay, so here's one big rule. So let me write this big rule. Treat underlined things, underlined numbers, like variables. So what do I mean by that? I mean, notice if I had 2x plus x in an equation, and I said simplify that equation, you would say, oh, that's easy. That simplifies to 3 times x, because I had 2 x's and one more x is 3 x's. We want to do the same thing here. So if I have 2 times 11 and 11's underlined, plus 11 and 11's underlined, then what I'm going to do is treat that as 3 11's. So I'm never going to multiply an underlined thing through. I'm never going to make this 33, because that would lose the data that I've stored. Think of it as like this underline is preserving that number for me in the computations. And doing this is going to allow us to get an answer here in the end. Because otherwise, if I just said, okay, well, this is 4 and 3, I'll just go ahead and do subtraction. What do I get? I get 1 equals 1, which is not very helpful. The reason this is going to be helpful is notice that my underlined things, 4 and 3, I have equations for it over here. And so I'm going to rewrite 3 in terms of 11's and 4's in a minute. And then I'm going to rewrite the 4's in terms of 15's and 11's. Then I'm going to rewrite the 11's in terms of 56's and 15's. And at the end, I'll have an equation with 1 on the right side and 56 times something and 15 times something on the left side, which exactly solves what I care about. So this is the trick. You really have to think of these underlines, or you could use a colored pencil for these numbers, but you really need to think of it not as 4, but like x4 and x3 and x1. Like they're new variables and they can't be combined with each other. We're not going to combine them. Okay. So that said, let's play the game. So what do? We took the very last line. Last line is important. We're going to go up. We wrote it down over here. And now let me check off. I've used that last line, and now I'm going to go to the second to the last line. And notice that the second to the last line has 3 equal to something, and I have a 3 in my equation. So I'm now going to perform the substitution using the last line. So this becomes, the 4 comes down, minus, and instead of 3, I'm going to substitute what I have on the left side of that equation. So it goes 11 minus 4 times 2 is equal to 1. And now let's put the minus sign through, so this becomes 4 minus 11 plus, and we can do 2 times 4 is equal to 1. And so notice, and I'll simplify before the next step. We have 1 4 here, 2 4's here, so this becomes 3 4's minus 11 is equal to 1. Okay, so far so good. And now I'm done with that line. Now I go up to the next line, and notice that the next line is in terms of 4. 4 is equal to something. And so I'm going to take my 4 in this equation and replace it with what it's equal to in this line of the Euclidean algorithm. So this becomes 3 times 15 minus 11, and we'll drop the times 1s. Times 1s we can just drop. So that I replace the 15 minus 11 with the 4 with the 15 minus 11. I still have to bring the rest of my equation down, so that's minus 11 is equal to 1. That brings the rest of it down. Multiply the 3 through, so this means I have 3 15s minus 3 11s minus another, we might want to put parentheses there, minus another 11 that is equal to 1. And so what do I have? I have 3 15s minus 3 11s minus 1 11, that's minus 4 11. So let's simplify 3 15s minus 4 11s is equal to 1. And now the final step is to use, so we've used this one. So we're working our way up the chain, and now we're at the very last one. And here I have things in terms of 11, so when you plug this in, so this becomes 3 15s minus 4, and I'm substituting in for the 11, I get...
I don't understand anything, to be honest.
ChatGPT. Examples. Explain quantum computing in simple terms. Right word arrow. Got any creative ideas for attention? The extended Euclidean algorithm is used to find the inverse of a number modulo n, where a and n are integers. The algorithm works by iteratively calculating the greatest common divisor of a and n, and using this to find a linear combination of a and n that equals the greatest common divisor. The algorithm starts by checking if a is 0. If it is, then the inverse is also 0. If a is not 0, the algorithm initializes variables lm, hello, and hi. Lm and are set to 1 and 0, respectively. The algorithm works by iteratively calculating the greatest common divisor of a and n, and using this to find a linear combination of a and n that equals the greatest common divisor. The algorithm starts by checking if a is 0. If it is, then the inverse is also 0. If a is not 0, the algorithm initializes variables lm, hello, and hi. Lm and are set to 1 and 0, respectively, and low and high are set to a% n and n, respectively. The algorithm then enters a loop that continues as long as low is greater than 1. In each iteration of the loop, the algorithm calculates the quotient r of high divided by low, and uses this to update the values of lm, low, and high according to the formulas JavaScript copy code n equals lm asterisk r, new equals high, low asterisk r, lm, low, high equals nm, new, lm, low. At the end of the loop, the algorithm returns lm%n, which is the inverse of a modulo n. The formula used to update lm and is based on the fact that the greatest common divisor of a and n can be expressed as a linear combination of a and n. CSS copy coded a n equals s asterisk a plus t asterisk n, where s and t are integer. The algorithm finds s and t by working backwards from the greatest common divisor to the original values of a and n. The variable lm is used to keep track of the coefficient s of a, and is used to keep track of the coefficient t of n. What is the point of this part of the code? Lm equals 1, 0. Low, high equals a% n, n. The code lm equals 1, 0, and low, high equals a%n, and initializes the variables used in the algorithm. Specifically, lm and are the coefficients used to express the greatest common divisor of a and n as a linear combination of a and n. Low and high are the remainders obtained when n is divided by a, and is divided by n, respectively. Setting lm equals 1 and equals 0 ensures that the first linear combination of a and n is a equals 1 asterisk a plus 0 asterisk. The values of low and high are set to the remainders obtained when n is divided by a and is divided by n, respectively, which are used in the main loop of the algorithm. By initializing these variables at the beginning of the algorithm can start working from the first remainder and iterate until it reaches the point where the remainder is 1 or 0 if a and n are not relatively prime. What is the point of r equals high slash low? The expression r equals high slash low calculates the integer quotient of high divided by low using integer division. In the context of the extended Euclidean algorithm, r represents the number of times that low fits into high without exceeding it. This quotient is used in the subsequent steps of the algorithm to update the values of lm, low, and high. Specifically, r is used to calculate the new value of low as new equals high, low asterisk r, which represents the remainder obtained when high is divided by. The formula for the new value of lm is nm equals lm asterisk r, which is used to update the coefficient of a in the linear combination of a and n that equals the greatest common divisor. By calculating r at the beginning of each iteration of the loop, the algorithm can use it to update the variables and move closer to finding the greatest common divisor of a and n.
I don't understand what is the point of doing this here. This is gonna become the new low here. I don't get it. I'm gonna have to spend a lot of time thinking about this. I'm struggling to understand what is the point of doing these things.
Extended Euclidean algorithm. In arithmetic and computer programming, the extended Euclidean algorithm is an extension to the Euclidean algorithm and computes, in addition to the greatest common divisor, GCD, of integers a and b, also the coefficients of Bezout's identity, which are integers x and y such that this is a certifying algorithm because the GCD is the only number that can simultaneously satisfy this equation and divide the inputs. It allows one to compute also, with almost no extra cost, the quotients of a and b by their greatest common divisor. Extended Euclidean algorithm also refers to a very similar algorithm for computing the polynomial greatest common divisor and the coefficients of Bezout's identity of two univariate polynomial. The extended Euclidean algorithm is
Hi everyone, in this video we're going to be talking about the extended Euclidean algorithm. This has applications in number theory, so lots of mathematics, and cryptography. So this is very useful for computing multiplicative inverses. We're going to get into that in a bit, but yeah, it's used in security and cryptography and encryption and decryption and all that good stuff. So this video is going to contain a lot of math and a lot of coding. Maybe not that intense, so don't get scared. But we have OneNote open over here as well as VS Code to do both the math and coding. So some preliminary knowledge. You might already know this, but we're just going to review it. GCD. This is the only bit of stuff we'll need to know prior to the video. So GCD of x and y, this is the greatest common divisor function. What it represents is the greatest integer that divides both x and y. So for instance, GCD of 2 and 12 equals 2. GCD of 15 and 35 equals 5. GCD of 12 and 30 equals 6, and so on. A special example of this is when GCD of x and y equals 1. We call this relatively prime. Specifically, we say that x and y are relatively prime. This means that they have no common divisors other than 1. Great examples are prime numbers. Prime numbers are relatively prime to most other integers. So for instance, GCD of 7 and 15 is 1. And GCD of 30 and 77 is also 1. So even though 30 and 77 are not prime, they don't share any divisors. So we say that the greatest common divisor is 1. So with those definitions out of the way, let's jump into the rest of the video. Now you may have heard of the Euclidean algorithm before. We will extend that a bit later into the video. But basically, its goal is to compute the greatest common divisor of two integers in an efficient way. So let's do an example. GCD of 12 and 30. We know that this equals 6 because 6 divides both 12 and 30, and no number larger than 6 divides both 12 and 30. So how are we going to compute this? Well, we're going to use a quite useful theorem. It's not really a theorem. It's not that complicated. It states that if D divides x and D divides y, then D divides x minus y. Now, if you think about this for a bit, it makes intuitive sense, but we can prove this rigorously. We don't really need to, but maybe this will help cement it in your mind. We can write x equals k times d for some integer k, and y equals m times d for some integer m, and then we have x minus y is kd minus md, which is equal to, if we factor out the d times k minus m. So this makes it very clear that x minus y is divisible by d. By the way, I'm using this notation, this pipe notation, to mean that one number divides another. So d divides x can be written as d pipe x. So with that theorem out of the way, we can actually do the Euclidean algorithm. Basically, how this works is we have GCD of 12 and 30, right? This is equal to the GCD of 12 and 30 minus 12, which is equal to, if we evaluate this, GCD of 12 and 18. We can take this a step further, so we can do 12, 6, and then we can start subtracting the other way. So GCD of 12 minus 6 and 6, which is GCD of 6 and 6, which is GCD of 6 minus 6 and 6, which is the GCD of 0 and 6. Once we get a 0 in a GCD, it's just going to be the other number because every number divides 0. So there's a very explicit way of describing the Euclidean algorithm. We're just subtracting the smaller number out of the bigger number until we get one of the numbers equal to 0, in which case we'll have the GCD as the other number. We can do another example, 13 and 30. We know that this equals 1 because 13 and 30 are relatively prime just by, experimentation. So how we can do this, we're going to improve on this algorithm a little bit. Instead of doing 30 minus 13 and then 17 minus 13, we're just going to do 30 mod 13. So we're just going to take the remainder when 30 is divided by 13 because repeated subtraction is the same as division. So if we're going to do 30 minus 13 anyway, we might as well just take the remainder when dividing by 13. Just get rid of all those 13s first and take what's left. So this percentage operator, if you're not familiar with it, just means remainder. So this evaluates to 4. So we can directly go to GCD of 13, 4. And then we can do it again, except 13 percentage 4. So the remainder when 13 is divided by 4 can take the place of 13. And this just becomes GCD of 1 and 4. And then we do GCD of 1, and the remainder when 4 is divided by 1, which is 0, at which point the algorithm terminates. So there's a brief description of the Euclidean algorithm. Hopefully you were already familiar with it. Now let's implement it in code. So we're going to define a function called GCD of x and y. What we're going to do is take the remainder of one number divided by the other continually. So while x is greater than 0, we're going to do xy is replaced by the remainder when y, and the remainder when x is divided by y. Now in Python, this is very nice because we can simply do one pair of numbers equals another pair of numbers, just assign those pairs to each other simultaneously without having to use temporary variables or anything like that. And once this loop is done, x is going to equal 0, so we can just return y. Now let's do an example. GCD of 12 and 30, that was our first example. Oh no, we have division by 0. Maybe this should really be while y is greater than 0, and then we can return x. Okay, great, we forgot to print it out. Classic coding tutorial. Okay. Great, it prints out 6. Now, you might be wondering, why does this work at all? Because we didn't really talk about the order of the numbers going in and coming out in this description over here. And this just works because while we're doing x and y, it doesn't matter which one is larger. The next step, it'll get replaced by y, and the remainder when x is divided by y. Now, this is great because the remainder when x is divided by y is guaranteed to be less than y. This just is a consequence of the division algorithm. Like if you do something divided by 12, n divided by 12, the remainder is going to be less than 12 because we're dividing by 12. So we are guaranteed that these numbers are shrinking as we go down. which means that one of them will eventually hit 0. So that's why this code works over here. It's nice and short, very concise. Okay, now let's talk about the extended Euclidean algorithm. Okay, our goal here is to determine the solution to an equation, this integer or Diophantine equation, if you like. A times x plus b times y is equal to GCD of a and b. Now, this equation is guaranteed to have a solution in integers a and b by Bézout's identity. They were some mathematician that lived in France, so I think this is a French name. I'm forgetting some accents, I'm sorry. But yeah, their theorem or identity guarantees that this equation has solutions in x and y given values of a and b. So let's do an example. I'm going to be using some extra variables. So we're going to introduce the variables q, r, s, and t. So at every step in this algorithm, we're going to have, let's label these as si, and this is the index I. This is the remainder at step I, and this is the quotient at step I. We're going to have si times x plus ti times y equals the remainder. Quick correction from future William. Here I mean si times a and ti times b, not x and y. So just keep in mind that equation should be a and b, not x and y. This is the important step because at the very end, we're going to get the remainder as 1, and then si and ti are going to be the coefficients of the initial constants that can be used to solve Bézout's identity. So initially, remainders are going to be set to the numbers themselves. Let's take 30 and 77. So first is 77 and 30. Now si is going to be 1 in the first step, and ti is going to be 0 in the first step. And then in the, well, by first step, I mean step 0. So then in step 1, si is going to be 0, and ti is going to equal 1. And now let's do the Euclidean algorithm as usual. So the quotient when 77 is divided by 30 is 2, and the remainder is 17. Now the corresponding equation for this, again, is 77 equals 2 times 30 plus 17. Notice that 2 and 17 are the quotients and remainder for this step, respectively. Alternatively, we can write this as 17 equals 77 minus 2 times 30. So we can now fill in si and ti. Si is going to be the coefficient of 77 to produce a remainder of 17, and ti is going to be the coefficient of 30. Si in this case is going to be 1, and ti is going to be
Let me
negative.
see if I'm understanding this. So it starts with 1 and 0 because it's the smallest. And then you want to work your way back to the greatest common divisor. Because in the worst case, it's going to be 1 and 0, I think. And then you do the whole thing about, which I'm still struggling to understand. You're getting the number and then subtracting the remainder times the quotients. I don't understand this part though. Like this multiplication here. Why are you multiplying the remainder with the quotients?
Of a and b. So let's do an example. I'm going to be using some extra variables. So we're going to introduce the variables q, r, s, and t. So at every step in this algorithm, we're going to have, let's label these as si, and this is the index I. This is the remainder at step I, and this is the quotient at step I. We're going to have si times x plus ti times y equals the remainder. Quick correction from future William. Here I mean si times a and ti times b, not x and y. So just keep in mind that equation should be a and b, not x and y. This is the important step because at the very end, we're going to get the remainder is 1, and then si and ti are going to be the coefficients of the initial constants that can be used to solve Bézou's identity. So initially, remainders are going to be set to the numbers themselves. Let's take 30 and 77. So first is 77 and 30. Now si is going to be 1 in the first step, and ti is going to be 0 in the first step. And then in the, well, by first step, I mean step 0. So then in step 1, si is going to be 0, and ti is going to equal 1. And now let's do the Euclidean algorithm as usual. So the quotient when 77 is divided by 30 is 2, and the remainder is 17. Now the corresponding equation for this, again, is 77.
And the quotient is true, the remainder is 17. So quotient here would be true, the remainder, which is low, would be 17. It's true times 17.
Equals 2 times 30 plus 17.
Yeah, that's the thing, is multiplying 2 times 30. Oh, but it is the remainder of the previous one then, maybe. Quotient is true. So this would be true. And then low is the remainder. So I think, yeah, it's the remainder of the previous one. And this high is the number itself. Yeah, but the number is not. That's the thing. I guess it's because this algorithm here is different than the way he's explaining there. That's why it's confusing.
Notice that 2 and 17 are the quotient and remainder for this step, respectively. Alternatively, we can write this as 17 equals 77 minus 2 times 30. So we can now fill in si and t. Si is going to be the coefficient of 77 to produce a remainder of 17, and ti is going to be the coefficient of 30. Si in this case is going to be 1, and ti is going to be negative 2. Yeah, we can continue on. Now in the third step, we're going to be dividing 30 by 17. That's going to be a quotient of 1 and a remainder of 13. We can rewrite it as 13 is equal to 30 minus 1 times 17. Notice how this 17 and 30 pops up as the previous remainders. Okay, now is the step where we kind of put everything together. So we have this very important equation over here. 13 is equal to 30 minus 1 times 17. We're going to write 30 and 17 in terms of 77 and 30. So we have 13 is equal to 30 minus 1 times 17. We can use the information in the table. 30 is equal to 0 times 77 plus 1 times 30, and 17 is equal to 1 times 77 minus 2 times 30. We can even write these as vectors. So 30 is 0, 1, and 17 is 1, negative 2. Now, 13 can be written as a linear combination of these two vectors. It is 1 times the first vector minus 1 times the second vector. And that just produces 0, 1 minus 1, negative 2, which becomes negative 1, 3, I believe. Now, what this really means is that 30 can be written as 0 times 77 plus 1 times 30 minus 1 times 77 plus 2 times 30. Combining like terms just gives negative 1 times 77 plus 3 times 30. And the coefficients of 77 and 30 are what we got in our vector thing down here. So we can fill in the table and write 13 as a linear combination of 77 and 30 using what we just computed. So the coefficient of 77 is going to be negative 1, and the coefficient of 30 is going to equal 3. Now we can sanity check this just by saying, okay, well we have negative 77 and 90, and together that does make 13. So far this makes sense. All right, we can move on. Now for step 4, we can sort of generalize what we had in the previous steps. So again, we're going to take the previous two remainders, 17 and 13. 17 divided by 13 is 1 with a remainder of 4. 4 is equal to 17 minus 1 times 13. And the original equation over here on the left was 17 equals 1 times 13 plus 4. Great. So now we just take those vector products again. 17 is 1, negative 2, and 13 is negative 1, 3. We multiply this one by -1, and we keep this one the same. And what we get is, I believe, 2, -5. Okay, great. We're not quite done yet because we don't have 0 for the remainder yet. So let's keep chugging along. Okay, great. Step 5. 13 divided by 4. So that's a remainder. That's a quotient of 3 and a remainder of 1. Let's actually start generalizing this step. So, actually, maybe we shouldn't generalize yet. I know this video is getting kind of long, but let's just complete the table for completeness. I mean, this video is really meant to be a reference. So SI is the coefficient of 77, and TI is the coefficient of 30. Let's write out that equation again. 13 is equal to 3 times 4 plus 1. So 1 is equal to 13 minus 3 times 4. Great. So again, we have our -1 and 3 vector, just written out like that, and the 2, -5, with a coefficient of -3 attached. Adding these two together gives, I think, -7 and 18. Let's double check that. So -7 times 77 is -539, if I'm not mistaken. And 18 times 30 is 540. Adding those two together does produce 1, so great. On the next step, this is quite unnecessary because one of the remainders is already 1, but let's just go through the motions anyway. 4 divided by 1, that's a quotient of 4 and a remainder of 0. At this point, we can just stop and use the entries for SI and TI in the previous row because we know the remainder is going to be the GCD of 77 and 30. So our answer is just x equals -7 and y equals 18. So our final solution to Bezout's identity is going to be, let me use consistent coloring, 30 times -7 plus 77 times 18 equals 1. So there we go. There we have our solutions for x and y. They are -7 and 18. So just writing out our final equation for Bezout's identity, we have 77 times -7 plus 30 times 18 is equal to 0. And that is our solution for all this work that we did. Now, how do we generalize? This is probably written better in code, but for a given step, qi plus 1 is just the previous remainder, I minus 1 over remainder I, taking the floor of, evidently. Remainder of I plus 1 is remainder of I minus 1 modulo remainder of I. Let's look at SI and TI. SI, or maybe I should write SI plus 1, is equal to 1 times the linear combination, that is SI of 2 prior, minus the quotient of I plus 1 times SI plus 1, I believe. No, SI. Similarly for TI, it's literally the same thing. I think these are our recurrence relations to get the next row of the table. Now, setting up the first two rows of the table is rather simple because we just have the first two numbers as well as SI and TI. I guess take a minute to pause and look at these equations, maybe rewind through the video if you need to. But kind of, yeah, get the idea of how SI and TI are really a vector representing the linear combination of the first two variables we have here, the first two constants, that's our a and b really, and how the quotient and remainder play into that. Okay, this video is getting quite long, so let's move into some implementation. I'm sure there are going to be bugs in the code, but you know, this is what coding is all about, debugging and trying stuff until it works. So let's make a table. Qi is going to be r of I minus 1, quotient of our I. So what we're doing here is we're just taking the second to last r and the last r, doing that quotient operation. R is going to be the same thing. I just realized we need to do integer division for q, not the modulus. Okay, now we have s. Yes, it is just the previous one, minus the new q times the s that was 2 before. T is going to be similar. Okay, and then at the very end, the last element of r is still not 0. We're going to be doing these 4 operations. And then the answer is going to be, I think s of -2, t of -2. So let's just do this example. On 77 and 30. I guarantee you there are going to be some bugs here. Oh, no, it just works. Okay, well, you know, it's not often that you get code that works like this on the first run. Okay, let's do a slightly unwieldier example. How about we do 260 and 52, 0, 1. Right, and this makes perfect sense, because if we have 0 times 260 plus 1 times 52, that's exactly the GCD of 260 and 52, since 260 is equal to 5 times 52.
The thing is that this algorithm is returning just one thing here as well. I'm trying to think about things, different ways to ask ChatGPT questions that are gonna help me clarify. But I can't think about anything. Maybe I should ask like what it does.
Hi, welcome to
So
this
perhaps that was a bad
video
example.
series
Let's do another one. Let's do 67
Today I'm
and
going to talk
56.
about another fundamental
Great. Okay, so this looks
algorithm
pretty
called
reasonable.
extended
We do
Euclidean
negative 5 times 67
algorithm.
plus 6 times 56. That should give us 1, which is their greatest common divisor. Okay, let's get into how this is actually useful. So we have this equation ax plus by equals GCD of a and b, and we have a very efficient way of computing integer solutions to this equation. So given a and b, how do we find x and y that are integers? So we have fast ways of solving this equation. Let's take a special case. Let's do GCD of a and b is equal to 1. So these are relatively prime now, and I think this is like the way we should do it anyway, because if we have GCD of a and b is greater than 1, then we can just do ax over that GCD plus by over that GCD equals 1. So we can just essentially scale down a and b anyway such that their GCD is 1. So how is this useful? We're going to be employing a thing called modular arithmetic. Now, maybe I should have done this in the definitions as well, but what we want basically is a solution to the equation ax plus by equals 1. We're really going to be solving for x here. We don't really care about y, because what we want is a solution to the equivalence. Ax is equivalent to 1 mod b. If you're not familiar with modular arithmetic, this is quite simple, really. It just means that the remainder when ax is divided by b is 1. Now, this is useful in cryptography when we want to find modular inverses, because when we're working under a modulus, we don't have division. We have addition and we have multiplication, and we have subtraction, which is really just inverse of addition, but we don't have the inverse of multiplication, at least not directly. So in theory, if a and b are relatively prime, so their GCD is 1, then there does exist a solution to this equation. In future videos, I might talk about RSA or whatever, which requires finding modular inverses, but to solve this equation, we need that ax minus 1 is equivalent to 0. So we need to do subtraction as usual, which means that ax minus 1 equals some integer y times b, which is just ax minus by equals 1. And we don't really care about the sign of this y, so we can just easily turn that into an ax plus b times negative y. So finding multiplicative inverses is really as simple as applying the extended Euclidean algorithm. Now that's all the applications we'll dive into today, but there are many more that I haven't covered in this video. So yeah, that's the extended Euclidean algorithm. It's a great way for finding solutions to Bezout's identity, as well as finding multiplicative inverses. So this code is obviously redundant. People have implemented this a million times.
Which is needed for cryptanalysis and cryptographic protocols, a very valuable algorithm. So the algorithm is actually built on top of Euclid's algorithm, which I talked about in the previous segment. So what is the goal of this segment? The goal of the segment is this. Suppose you're given two numbers a and b. Okay, you're given two numbers a and b, integers a and b. Both of them are not zero simultaneously. One can be zero. Your goal is to find two numbers x and y, in fact three numbers actually, and a d, which satisfies this interesting property that a times x plus b times y equal to d. Okay, it's kind of it's a linear equation with two variables to the left and one variable to the right. Okay, what is d? D is nothing but GCD of a and b. GCD is the greatest common divisor that I talked about earlier, so I will not talk again. I encourage you to watch that video. Okay, so now how do we find these numbers x and y and d from a and b? We know how to find d from a and b. This is basic Euclidean algorithm. However, we need to also now find a and b. There are many books that talk about extended Euclidean algorithm in great detail, and there are a lot of valuable materials online. I'm a little bit confused at times when I see a lot of complex while loops and a lot of variables. So I thought I will take a step back and see whether I can come up with some simple recursive notion of extended Euclidean algorithm. I'm not claiming anything new here. It could be present already. So what I'm going to talk about is a recursive algorithm to solve this problem. Okay. So let me start with the very basic case. What if my b is 0? Well, if my b is 0, the answer is easy. My b is 0 means I can take my x to be 1 and then my d to be a, then I'm done, right? Since b is 0, I can pick whatever value of y I like, because b times y will cancel out. So this solves the problem. Any y will satisfy this equation. Okay, so what I'm going to do though is consider the case that we can rewrite the original problem into subproblems and then use recursion for that. Okay, so what I'm going to do is try something like this. Try something using my algorithm here. So what I'm going to do is I will rewrite this GCD problem into a subproblem as follows. Instead of computing GCD of a and b, we will go ahead and compute GCD of a subproblem, which is GCD of b and r. Okay, what is r? R is r is nothing but a mod b, right? Or the reminder when a is divided by b. This is something true from Euclidean algorithm. We have seen this. Okay, now let's assume magically we found out x1 and y1, which satisfy this property. B times, or from this, let's assume we found out magically two pairs x1, y1 like this. Okay, is equal to d. Remember, GCD of a comma b is same as GCD of b comma r. So this must be d then. Okay, suppose we found out this. How can we now use this to solve the original problem? The original problem is dealing with a and b. Okay, here we have a b, that's good, but we don't have a here, so we need an a somehow. So how do we get rid of r? It turned out that we can use another interesting property. Suppose we can rewrite our a like this. Okay, a is 2 times b plus r. Okay, this is true when a is an integer. We can always find another integer q and r which satisfy this property. Okay, what is r? R is basically the reminder when a is divided by b. So r has to be bounded by the value of b. Okay, so we can now rewrite r as nothing but a minus qb. Okay, so our r is now gone. We can now go back to this equation and simply replace r by a minus qb, and then just to rewrite it a little bit, we will get something like y1 times a plus x1 minus y1 times q, okay, times b is equal to b. So we got what we wanted, right? We need something adjacent to a. Yes, we have for a is y1. Something adjacent to b. Yes, this part is for b. Okay, so the solution is simple now. The solution is x is equal to y1, right? And y is equal to x1 minus y1 times q. Okay, so we do know everything. We know how to compute q, we know how to compute r, therefore we can compute everything, but we still haven't figured out how to find x1 and y1. So we let the recursion go all the way until the case that our reminder becomes 0. At that point, we do know exactly what answer is. As I said earlier, when you compute GCD, okay, you're recursively computing smaller and smaller pairs of values, and r becomes eventually 0, then that time you stop. Okay, when you have a situation like this, let's take this example again, right? A comma 0. What is GCD of this? This is nothing but a. Okay, that means my x has to be 1, and y can be anything I like, whatever value you like. So I put a question mark, and d is nothing but a. So we found out the value of x and y. When one of the arguments is 0, it's straightforward. Okay, and that will become true when this recursion is triggered, right? And what's the next step of this recursion? Next step of this recursion is GCD of r, which is smaller than b, and then b percentage r mod r or division of b by r. So if you continue this, at some point this second argument will become 0. At the time, we know the value of x and y, and then we use that to build the next level of x and y. So that's why I said here, if you magically solve the subproblem of b and r, we get x1 y1, and then we just take x to be y1 and y to be x1 minus q1 times q. That's basically it. So I will now show you a quick implementation of this idea. Very simple and neat idea. Okay. So what I'm going to show you today is just to show the algorithm that's going to implement that part. Okay. So here's the recursive algorithm. I'll zoom in a little bit. So the algorithm takes a and b as inputs and computes x and y and d, which satisfies this property a times x plus b times y is d. Okay. What is d? D is nothing but GCD of a comma b. So as I said earlier, it's very simple when b is 0, right? When b is 0, all you're going to do is you treat your x to be 1 and y to be 0. And by the way, y can be any value, as I said. You can change the y, doesn't matter. Okay. And your GCD is of course a when b is 0. Therefore, you solve the subproblem. Now the high-level problem is if b is not equal to 0, you compute the extended GCD algorithm for b comma a percentage b. Once you solve that, you find a new x and y, exactly like the way I explained on the whiteboard. You compute the quotient, you use x to be y1 and y to be x1 minus y1 times q, and you can even have an assert statement that checks that your algorithm is correct. Okay. So this is basically it. And now I can show you some implementation, some runs. I will start my Python from my program name is xgcd. I will import all of things, and I will just call my recursive version of extended GCD because I also wrote a non-recursive version, but that's a little bit more complicated than the recursive version. I will compute the recursive extended algorithm for 8 and 12. Right? What are the things I will be getting? Because minus 8 plus 12 is 4, and d is 4. So we can also pretty neat. All you're doing is calling the extended Euclidean algorithm and then computing x mod b, and then you get that sort of result. Okay. The reason is simple, right? A times x plus b times y is 1. So ax is 1 minus by, and ax is equal to 1 mod b. That's the reason for 1 minus mod b. Okay, this comes directly from the definition of a mod, these two, right? That means the x must be multiplicated inverse of a. So all you have to do is just call the extended Euclidean algorithm. Here I'm using both recursive and non-recursive. So in my code, I have this is non-recursive, which you can see non-recursive GCD is a bit involved. It requires a couple of more variables, and then you need to keep track of the last two state. Yeah, it's basically the same more or less, but it's still a fair amount of more work comparing to recursive version. And the recursive version is very straightforward, coming from the structure of how we are sort of solving a larger problem by using a simple solving a smaller subproblem and then making use of the result. Like
Okay, in this video, we're looking at the notion of multiplicative inverse
comma a mod b first and find the x1 y1 and then use that to compute your x and y for the larger problem. Okay, so that's basically the main point I would like to convey to you. Thank you very much.
Okay, so we're doing inverse mod numbers. So we'll start with the example 17x is equivalent to 1 mod 43. Now it's just asking what number times 17 will give you 1 when it's mod 43. So to get x on its own, we just take 17 over the other side. So that'll give us 1 over 17 mod 43. And that's just the same as saying x is equivalent to 17 to the power of negative 1 mod 43. Now to work that out, we use the Euclidean algorithm and the extended Euclidean algorithm. So we start off with this 43 here, and that'll be equal to 17 times what, which is 2, plus 9. And then we want to underline these two here, just so we remember that those are the two that we want to bring down next time. So then we bring this 17 down, bring the 9 down. And so that's times what number, which is obviously 1, and then plus 8. Underline them again, okay, and then bring the 9 down, bring the 8 down, and that's obviously times 1 plus 1. Now when we get a 1 in this position, that means that the GCD of 43 and 17 is 1. We can only ever find an inverse number when this GCD is 1, otherwise you can't do it. So in this case it is 1, so we can continue. So now we want to move on to the extended Euclidean algorithm. So to do that, we want to write this term here in terms of, sorry, this equation here in terms of 1. So we want 1 equals, now to get that on its own, we just take this 8 times 1 over the other side. So we get 9 minus 8, and then it's times 1, but we can just leave that off because it's the same as saying 8. Okay, so now we want to sub in. We've already worked with this equation, so we want to work back up the Euclidean algorithm, and we want
Shit is so confusing. I don't understand what it's NM supposed to be. And it's gonna update this LM. Doesn't make any sense for me. I think this part is more like it can make more sense based on the stuff she's talking about there. You have the full number minus, but it is still hard to understand. I guess this part is just n minus n minus. I think I confused myself there. don't know, it's because low, I guess high is gonna be this thing here, or high is gonna be n, and low is gonna be this. So it is the way that it was written there. It's so confusing. I don't understand how this, like, I know it is supposed to be similar to what she's talking about here, but I can't make the connection there. Like 9 is the remainder, and then the multiplication, the number here is the full division, like the quotients. So this is the quotient plus the remainder is gonna be equal to the number here. But what does this have to do with this thing? It seems like like it's not connected. It's hard to understand why they did it like this here. As because the A and N is confusing as well. The problem is that the explanation of ChatGPT is not helping me understand. Because I'm having a hard time trying to understand the bigger picture of like what is going on each iteration. Angular multiplier inverse of a number. If they're relatively prime, it means that they are only divisible by 1. The greatest common divisor is 1.
Hey everybody, this is Paul. So in this video, I'm going to do an example.
We want to sub in this equation here. Now we want it in terms of this number on the end again. So same as we did before, just take this 9 times 1 over the other side. So that gives us 17 minus 9, again times 1, but we can just leave it off because it's the same. So we want to sub this equation into this one just above it. So we'll get 1 equals 9 minus, where there's an 8, you want to put this 17 minus 9. And then we can just simplify that. Negative and a negative make a positive. And we can simplify that one again. We've got a 9 and a 9, so that makes 2 times 9. And then minus 17. Okay, so now we've already subbed in here this equation. So we want to go back up the Euclidean algorithm and we want to use this one instead. So we want to sub that into what we've just done. So again, we want it in terms of this 9 here. So that'll make it sub 9 equals, take this 17 times 2 over the other side. So we get 43 minus 17 times 2. Now we want to sub this one into the one before it. So that makes 1 equals 2 times, instead of a 9, we want to write this equation here. And then don't forget this minus 17 as well. Okay, and then we can just expand that one out. So we've got 2 times 43. And then because this 17 is in the original equation, we want to keep it in terms of that 17. So we've got negative 17 times 2, and then times 2 again. So that is the same as saying negative 4 times 17. And then we also have this extra minus 17. So we can simplify that again. So 2 times 43. We've got a negative 4 times 17 and a negative 1 times 17. So that's negative 5 times 17. Okay, and so we've got our equation in terms of 43 and 17. Now, because the original question was mod 43, anything times 43, mod 43, is going to be 0. So in this bottom equation here, when we have 2 times 43 there, it's going to equal 0 because it's mod 43. So we can just cross that out, and then it's just whatever number is attached to the 17 here, because that's what was in the original question. So we've got 17 to the power of minus 1, mod 43, is equivalent to negative 5. Now, we want that between 0 and 42, because it's mod 43, so that is equivalent to 38. So when the original question asked 17x is equivalent to 1 mod 43, then our x equals 38. And that's it. That's how you do it.
Okay, in this video we want to look at how to find inverses module n. Not when they exist, that was done in a previous video, but exactly how to find them. So we'll give 2 main examples. One where the number n is kind of small and you can guess and check the inverses, and another where you have to do the extended Euclidean algorithm. Okay, good. So let's start with the one that is small. So let's find all inverse pairs mod 20. Okay, great. So again, from a previous video, we know that the invertible numbers mod 20 are the following. So we have 1, so it's going to be everything that's relatively prime to 20. So 20 has prime factors 2 and 5, so it should be fairly easy to write down a list. So we have 1, 3, so we can't have 5 because that's a multiple of 20. So 7 is next, 9 is next. So notice I'm skipping all the even numbers. 11 is next, 13 is after that. We skip 15, 17, and 19. So now let's get started with the kind of easy ones. So notice 1 is its own inverse, so we can write that down. 1 inverse is congruent to 1 mod 20. That will always be the case. Now we work up from there. So 3 times 7 is 21, and so 21 is 1 mod 20, so that's lucky. So 3 inverse is congruent to 7 mod 20, and likewise 7 inverse is congruent to 3 mod 20, so we won't write that down, but this inverse relationship is mutual. Now let's move up to 9. So 9 times 9 is 81, which is 1 more than a multiple of 20, so we have 9 inverse is congruent to 9 mod 20. So 9 is its own inverse. Great, and now we get into the numbers that are a little bit bigger and might be a bit trickier to figure out. So let's go to 11. So 11 times 11 is 121. Oh, but luckily 121 is 1 more than a multiple of 20, so that means 11 inverse is congruent to 11 mod 20. Okay, fantastic. Now we're going to use a trick for 13,
I
17.
don't understand why this is the case. I think I'm struggling to understand this modular arithmetic thing. Like when I think about this mod, I think one, like the thing that is on the left divided by the number here and the remainder of that. But 1 divided by 20 would be a broken down number. So why is the remainder 1? I guess it's because you can't divide it. But then 3 is 7, so it was 1/3 divided by 20. That's 20 divided by 3. And that doesn't make sense. Yeah, I don't understand.
And 19, and we'll start with 19 even though that's the largest number. So what we'll do is we'll notice that 19 is congruent to -1 mod 20, which tells us that 19 times 19 is congruent to -1 squared, which is congruent to 1 mod 20. So that means 19 inverse is congruent to 19 mod 20. So we'll work with the negative numbers, and it makes it a little bit easier because we can work with smaller negative numbers. Now we'll do the same thing for 13 and 17. So notice that 17 is congruent to -3 mod 20, and 13 is congruent to -7 mod 20. Now when we multiply -3 and -7, we get a positive 21, which is congruent to 1 mod 20. So let's write that down. So 17 times 13 is congruent to -3 times -7, which is 21, which is 1 mod 20. Good. And finally, what that tells us is that 13 inverse is congruent to 17 mod 20. So in other words, 13 and 17 are inverse pairs mod 20. Okay, good. So with a number like 20, it's not so hard to guess and check the inverses. So let's look at another example where we have to do a little more calculation. Okay, so now we want to look at this slightly more difficult problem, which is finding 34 inverse mod 143. So we're going to use the fact that there exist integers x and y such that 34x plus a times y equals 1. And so we had it checked here that 34 and 143 are relatively prime, and we'll see that along the calculation. And so we'll use this fact, and then we'll notice that this x value that we find will be 34 inverse, because 34 times that x value will be, and I should put here, this is 143 times y. Will be congruent to 1 mod 143. Great, so since we're going for that equation, we need to use the extended Euclidean algorithm. So let's start and write 143 and the division algorithm with 34. So there are several videos where we do this in the past, and it's a fairly routine calculation, although it can get tricky if there's a lot of steps. So this is 4 times 34 plus 7. Good. Now we're going to take 34, that's going to go over here. We're going to take 7, that's going to go over here. We can write 34 as 4 times 7.
Doing like this is easy, but then thinking about the general approach and then the loop there. Like the thing is that this algorithm doesn't seem like this equation here is the one that they are using here. And this is what I don't understand. I guess it's just more confusing because of the way that it's written here, and I don't understand what each variable is supposed to be there in relationship to the examples that I'm seeing on the videos.
Plus 6. Okay, good. And then our 7 is going to go over here, and our 6 is going to go over here. We can write 7 as 1 times 6 plus 1. And so there we go, we get 1. Obviously 1 is going to be the last non-zero remainder, which tells us that 1 is the GCD of these two. In other words, the GCD of 34 and 143 equals 1. These numbers are relatively prime, which is a requirement for such an inverse to exist. Okay, great. So the next thing we do is we rewrite these equations. So we're going to solve for the remainders. So here we'll get 1 equals 7 minus 1 times 6. Good. And here we'll get 6 equals 34 minus 4 times 7. Okay, good. And then finally here, we'll get 7 equals 143 minus 4 times 34. Good. And then if you recall from previous videos, what we'll do is we'll take this expression for 7 and plug it into the value of 7 in the bottom equation. And what we'll see that we get here is the following. 17 times 34, so this is 17 times 34 minus 4 times 143. So minus 4 times 143. So that's what we end up with when we do that. Great. And now the next thing that we'll do is take this number for 6 and this expression for 7 and plug it in below. And we'll end up with 1 equals, so I'm skipping lots of arithmetic here, but again, look at another video if you want that. So this is 5 times 143 minus 21 times 34. Good. And now what we can do is rewrite that as follows. We can rewrite 34 times negative 21 is equal to 1 minus 5 times 143. Good. And now notice that number is obviously congruent to 1 modulo 143. Good. And that tells us that 34 inverse is equal to negative 21 mod 143. But we'd rather not work with negative numbers, so what we can do is just add a multiple of 143 to this. And what we'll end up with is that this is congruent to 122 mod 143. So 34 inverse is 122 mod 143. Okay, that's the end of this example.
I think I'm gonna study this stuff off stream, to be honest. It's gonna take me some time to understand this, and I have to stop and just spend time thinking about it without saying anything. And while I'm streaming, I feel the pressure to say or do things. So it's making it harder to concentrate and understand. I think it's better if I try to figure out off stream, and then once I have a good idea, then I come back and explain it and write about it. I think that's a better thing to do. It seems so confusing to me. I don't understand how, like, each variable, what it is supposed to be, and how does relate to the examples that I'm seeing there. Like, it feels like I'm not gonna get anywhere if I don't stop to think about or to understand more the other stuff. Yeah, I'm gonna stop here and might come back today, depending on how. I think I'm gonna look into the other things as well that are involved with this, like this modular multiplicative inverse, and try to like have a better intuition of how it works, and try to figure this out. And then once I have a better idea of how it works, then I come back and explain. So yeah, probably depends on how long it's gonna take. I don't know. But I might come back today later and then just continue. But the goal is going to be to explain this algorithm here, and I'm going to try to explain it as best as I can, step by step, once I understand how it works. And I think the rest I'm probably going to leave like it is here. The explanation there is good. Like the explanation in the beginning is easy to understand. Like the greatest common denominator should be equal to this Bezout's identity, which is just the multiplication of the two numbers. Like finding what numbers would multiply both of the numbers, and you would get the greatest common divisor. That's the whole thing. But like this here is very confusing to me. So I'm gonna try to explain this, and then after that I think I'm gonna read these articles again, and then to remember where this stuff is used in the Ethereum code, and then try to understand the algorithm in the context of Ethereum, and this Stark, which is a zero knowledge proof. So yeah. So if I don't come back today, probably tomorrow I'll come back. So